Alright, we're going to talk about reflection and refraction. We're entering the part of light where we talk about what we call geometric optics. Okay. When a light ray or light wave is incident on a smooth surface, that just means it strikes a smooth surface. Part of the wave is reflected. Think of a light hitting a piece of glass. And part is transmitted. Another word we're going to use for transmitted is refracted. So if you think of sunlight hitting a window, part of that sunlight will actually reflect off that pane of glass, but part of that light will be transmitted and pass through that pane of glass. Let's think about this. Let's try to draw some pictures. It's a little tricky on the whiteboard, but let's see what we can do. So let's that be our pane of glass. I have no idea how good I'm going to do at getting a normal draw, but I'm going to try. So here is a perpendicular. So maybe this side is air, this side is glass, it could be water, it could be a lot of things. But we have a ray, and I probably should not have even tried to draw that first, but I'm going to, let's see. Bear with me while I work on my art skills here. Here comes an incoming ray of light. It hits that glass surface, and two things happen. Some of that light just hits it and bounces right back off, and some of that light enters. And interesting enough, the light that enters also tends to be bent. It no longer travels in that straight line. So this is our incident ray. This will be our reflected ray. This would be the refracted ray. The dotted line here, of course, is the normal. And this interface between air and glass is usually called a boundary. It's a boundary between two different mediums. We measure all of our angles from the normal. The incident ray we are going to call theta A, and the refracted ray, we measure it from the normal also. We are going to call theta B, and the reflected ray, we're going to call theta R. Just to be consistent with what the labeling looks like in your textbook, the incident and the refracted, that's A and B. The reflected ray, we're just going to call theta R. Now, when light hits a surface, whether it's something like glass or whether it's something like water or even just the wall in a room, there's basically two kind of broad categories of reflection. One is called specular reflection. Specular reflection occurs when light strikes a very smooth surface. Think of things like glass and mirrors. When you get specular reflection, the light is reflected in a very definite, very predictable manner, and as a result, specular reflection forms clear images. You can see your face in a mirror or on a smooth pond. What happens essentially, I'm going to try once again to see how good I do on just drawing straight lines. Oh, nope, not where I wanted it. I want it down here. Maybe this will be straight, maybe not. Not too bad. So light comes in, and let's draw some parallel rays. And we have these parallel rays. If the surface is very smooth, those rays are going to reflect in a very predictable manner. And I really didn't draw my angles right there, but you get the idea. That's one type. The other type of reflection is called diffuse. This is the more common type of reflection. Most things on a microscopic level are not really that smooth. I'm sitting here with a black tablet in front of me. That black tablet that I'm touching feels pretty smooth, but if I were to examine it closer, I'd see that it was slightly rough. In this case, we get no clear images. So with diffuse reflection, even if we start with some nice parallel rays coming in, there's my nice parallel rays coming in. Oh, and I shouldn't have even used a ruler. On a microscopic level, this isn't smooth like glass. It may feel pretty smooth, but it's not. And as a result, they don't all bounce off in that predictable, definite angle. This one may be going off like this, but this one may go off like that, and this one may go off like that. You don't form a clear image. So when you look at your bedroom wall, you don't see your reflection of your face, even though light is reflecting off the wall. It's just not going to form that type of image. All right. Now, when the light gets transmitted into another medium, it actually travels at different speeds, and we categorize different mediums, different optical materials, by something called the index of refraction. And this only applies to optical materials. By definition, the index of refraction N is equal to C over V. C is the speed of light. In a vacuum. We already know what that is. That's at 3.00 times 10 to the 8th meters per second. And V is equal to the speed of light in the material. Notice they're going to have the same units. So if you're thinking meters per second, that actually cancels out. The index of refraction is a pure number. N will always be greater than 1 because the speed of light will always be the fastest speed. Nothing travels faster than the speed of light. In your textbook, if you look at table 23.1, there'll be a list of indexes of refraction, but here's just kind of a few just to think about. Light travels through air at almost the same speed it travels through a vacuum. For air, N would be 1.00. If we want to get it to actually be a little different, we have to go farther out. We are going to use 1.00 because we just are not going to have that many significant digits. Even if we wanted 4 significant digits, it would still be 1.000. Water is a common optical material. It has an index of refraction of 1.33. Quartz is 1.54. And a diamond, probably the most optically dense material you are familiar with, has an index of refraction of about 2.42. If you know how fast light travels, you can find the index of refraction. Or if you know the index of refraction, you could calculate how fast light travels. For example, if you wanted to find the speed of light or any electromagnetic wave, doesn't have to be visible light. In water, we know that N is C over V, or we could rearrange that and say that the speed in the material is C divided by N. So 3.00 times 10 to the 8th meters per second divided by 1.33. You get a calculator. And it comes out to be about 2.25 or 2.26 times 10 to the 8th meters per second. It's about roughly 3/4 of the speed that it travels through air or through a vacuum. Okay, let's start putting together. Here are the big principles of geometric optics. First of all of the rays lie in the same plane. The incident, reflected, and refracted rays and the normal, which is not a ray at all, all lie in the same plane. That certainly makes things a little bit easier than some of the stuff we were dealing with when we were working with magnetism. Makes it easy to draw. 2, and this is an easy one, this is called the law of reflection. And the law of reflection is very simple. It simply states that the angle of incidence is equal to the angle of reflection. Or if we want to use our shortened version, theta A is equal to theta R. We had that law before when we talked about waves. This isn't just true for light waves, it's true for sound waves or water waves or anytime you have a wave. So it's a pretty easy concept. The third big principle is the law of I'm sorry, that is not what it is. The third big principle is Snell's law. Now, sometimes this might be called the law of refraction. And it's usually written as NA sine theta A equals NB sine theta B. So this side is the incident material and the incident angle. This side, of course, is the refracted material and the refracted angle. Okay. That's the only three principles that the book has, but I've added kind of a fourth one, and I don't know whether I should call it the fourth or 3.5. I'm just going to call it 4. And that is simply that the path of light is reversible. And we'll look at that when we do some of the examples of the problems, and you'll understand better what I mean when I say that the path of light is reversible. Consider what happens when light travels from a less optically dense basically is another way of saying smaller index of refraction into a more optically dense medium. Another way you can think about it, less optically dense is a faster medium. Air is a fast medium. So this is an example. When you go from a less optically dense into a more optically dense, you might be considering going air into water. When that happens, when you go from a less optically dense into a more optically dense angle, the ray refracts, which is another way of saying bends, toward the normal. So for example, if this is our boundary, now let me draw the boundary, instead of drawing it vertically, just to mix it up, let's draw the boundary horizontally. Here's our boundary, and pretend it's straight. So maybe up here is air, maybe down here is water. Doesn't have to be. Here is an incoming ray, and it comes. So here's the normal. We measure from the normal, so this is theta A. Here's the refracted. It's going to go off like this. That's theta R, okay? But the reflected ray does not form a straight line. It doesn't keep passing in straight, like if you picture it going straight. It bends toward the normal. Oh, I picked up a new color. So this is theta B. When it goes to a more optically dense, another way of thinking that is a slower medium, it bends towards the normal. Now, what did I mean when I said it was reversible? Well, basically, if you look at Snell's law, let's go back and look at Snell's law. NA sine theta A equals NB sine theta B. If this was our incident medium, we would call this A and B, but the path would go like this, then this. Instead, it would actually go away from the normal. So if we reverse this idea, when light travels from a higher end, that's the more dense, slower material, into a lower end, it refracts away from the normal. I can illustrate that with the same picture almost. So here's our surface, but now instead of having air and water, well, let's consider glass with N equal 1.5 roughly, and water, N equal 1.33. Okay, if we start off with the material, well, I better draw the ray before I draw the normal. It's easier to get the normal right that way. If I start off with an incoming ray now, again, here's the normal. That's our angle A. Part of the ray will reflect, and the part that reflects is going to go off at theta R. Theta R and theta A are going to be the same, but part of it's going to be refracted. And there again, it won't follow, like if you think of a straight line, it's not going to go in a straight line. It's going to refract away from the normal this time because it's going into a lower index of refraction. This is theta B. Again, if we started in this material, this would be our incident index of refraction, this would be our incident angle, and you would see it would refract toward the normal. The path works both ways. The intensities, or the intensity, let's just say, of the refracted and the reflected depend on the angle. At small angles, most of the ray is transmitted or refracted. Again, we can draw our surface either way, but let's think about the surface of a lake. Something smooth like this. Light that's shining almost straight down. Well, change color. If a light ray, in fact, if a light ray is coming straight at it, like this, it tends to be virtually 100% refracted. But even if it's coming in at a small angle, let this be the normal. If our incident angle, theta A, is really small, most of it's going to get refracted. Keep right on going. It's going to bend just a little towards the normal. I always think about that. Think about a pond and a rock. If you drop the rock straight down, it's going to fall straight to the bottom. But those of you that have skipped stones know that if you get the right rock, if you come in shallow, this is a very large angle, you will get most of the light will actually be reflected. Doesn't mean that none of the light will be in. Some of it will still go this way and it will still refract. But the intensity here, you're going to have a much higher intensity of reflection. There's not going to be any quantitative aspect to this. I just want you to know that as the angle of incidence increases, more and more of the light is going to be reflected. All right, we've already stated the fact that when light travels from one medium to another, the speed changes. It's either going to speed up or slow down depending on what it's traveling. The speed changes. Why? Remember when we studied waves earlier? The speed of a wave really just depends on the medium. But the frequency stays the same. That was true with mechanical waves. Speed depends on medium. Frequency doesn't depend on the medium, but the frequency depends on the source, what's causing the wave. Okay, so think about what that means. We know that the speed v is equal to the frequency times the wavelength. That's our old wave rule we've been using all along. So in a vacuum, that velocity, we get c equals f lambda 0. Lambda 0 is the wavelength in a vacuum. And v equals f lambda. In this case, lambda is the wavelength in the material. Well, think about our index of refraction. Our index of refraction is simply c over v, which would be f lambda 0 over f lambda. And we see that we get a new ratio that the index of refraction is also the ratio of the wavelength in the vacuum compared to the wavelength in the medium. If this wave slows down, look at the formula. If V changes and F does not change, then the wavelength changes. So if the speed decreases, the wavelength gets shorter. If we think about that, let's consider a wave traveling. Here's our boundary. And again, we'll let this be air. That's a relatively fast material. We'll let this be glass, a relatively slower material. If the light wave looks like this, when it's entering with a certain wavelength, it doesn't change frequency, but it does slow down. And the result of this slowing is you can see that our wavelength changes. This was lambda 0, whereas this is lambda in the material. Let's do a problem. Whoops, sorry about that. Suppose that we've got an interface or boundary between water and air. Pretend my line is straighter than it is. Here's the air, here's the water. And underneath the water is a little fish. Put that little fish a little farther under the water. Here's a little fish. And light rays come off this little fish and hit the water. And when that happens, remember, here's our normal. They're going to refract, but they're going to refract away from the normal because it's going into faster medium. Goes into something faster, it bends away. So it bends a little like this. If you're the observer and you're looking at this fish underwater, there you are, you're looking. Where do you think the fish is? Well, your brain thinks light travels in straight lines because through the air it does travel. Your brain tracks that fish to right about here. Some people say that's an optical illusion. But the light bends. So the result of that bending light ray is you think the fish is here, but the fish is actually here. I can show you with some numbers. If I tell you that this is n equal 1.00, this is n equal 1.33, let's suppose that this angle is 30 degrees. What's this angle? So that's an example for Snell's law. NA sine theta A equals NB sine theta B. The incident, this is the incident side down here. We're starting with a light ray coming off a fish, and of course this is the refracted side. So we have 1.33 sine 30 equal 1.00 sine theta B. We have to actually do a sine inverse to get theta B. Theta B is going to be, if you multiply this out and divide by 1.33 sine 30 is 0.665. So theta B is equal to the sine inverse of 0.665. So sine inverse 0.665. And I get that the refracted angle is 41.7 degrees. So even though the fish is actually along this path, this angle right here is, what did we just get? 41.7? 41.7, 42 degrees. That's the path that your eye follows. Your eye thinks it's located along here. Do another example. Suppose we've got a laser, it's a red laser, that has a wavelength lambda that is 633 nanometers in air. It says the wavelength changes to 474 nanometers in the vitreous humor of the eye. Now, for those of you that haven't taken an anatomy class, the vitreous humor of the eye is the liquid jelly, kind of like a gelatinous fluid that's inside the eyeball. Okay? It says, find N, F, and V for the red light in the eye. I hope this is not a very strong laser. Lasers can be really damaging to the eye. Well, first of all, the frequency is going to be the same in air or in the eye. So frequency would be really easy to find. N will be really easy to find. Air is the same as a vacuum as far as we treat it. So this is going to be our lambda 0. So the index of refraction is lambda 0 over lambda. So 633 nanometers, 474 nanometers, 633 divided by 474 is 1.34. Notice that's almost identical to the index of refraction of water. That's not terribly surprising. The frequency of the light, F, we can just use C equals F lambda 0. We know the frequency is the same regardless of whether we are in air or in the eye, so we can just pick one of those to use. So frequency is C over. So 3.00 times 10 to the 8th meters per second. 633 times 10 to the negative 9 meters. And I get that the frequency is 4.74 times 10 to the 14th hertz. There's our index of refraction. There's our frequency. The speed of light, of course, we can do a couple of ways. I would go back to just using the original. We know that it's going to be the speed of light divided by the index of refraction. So 3.00 times 10 to the 8th meters per second divided by 1.34. It comes out to be 2.25 times 10 to the 8th meters per second. We'll do a lot more examples when we are in class together of look at using these rules. I'm going to cover one more section in this video, and that's section 23.8, total internal reflection. We know that when light travels, all right, I'm going to go ahead and stop. I think I'm going to save this for its own video. So let's just stop here. And we will pick up at this spot next video.